Hi everyone, my name is Yoav, my partner is Ido. Our project is focused on diffusion models based on different architectures, MLP, CNN, and transformers. We want to compare their performance on solving a point maze to MPPI, which is a classic algorithm that we'll explain about in the next slides. Let's discuss what is the motivation to our project and what the problems that we try to solve. So the problem is that robotic control requires controllers that looks ahead for the next steps and actions that will give us the trajectory to solve the maze. MPPI is iterative robotic planning algorithm that starts from random initial guess. So it's converged to a good solution but can be slow. In the other side, it's very safe. With enough iteration, we'll reach a good solution. Diffusion can give us and generate a good initial guess very quickly. So we want to combine them. We want to try to give from the diffusion warm start to the MPPI to improve the performance and evaluate it on different architectures and compare the results. Let's see the environment of the maze. We have a two-dimensional maze that the state of each time is the XY position and the XY velocities, but we can control in the action on the position of the ball, can only control the acceleration in the both axes. And the dataset that we use to train our model is the offline trajectories. And we want to find what is the best method to solve and to create the fastest trajectories that will bring the ball to the target. You can see here in the picture in the blue trajectory, the actions that we already took. And in the green is the next action that the model predicts that will bring the ball in the fastest way to the solution. Let's see how MPPI controller works. So the first step is to initial random trajectory guess. After it, we sample n action trajectories around this initial guess. So we can calculate according to dynamic cost function what is the cost of each one of the trajectories. Based on the cost, we can find what is the weighted average that we want of all these trajectories. So we can perform the n actions from this calculated trajectory. So even that the MPPI in our project calculate the trajectory of 100 actions, we will take only 5 or 10 from the first action and then recalculate the process again and again. In this slide, we will see what is diffusion and how it helps us to find the trajectory to solve the maze. So we can see in the video that we start from random noise, and after denoise step, we converge to the trajectory to solve the maze. So let's see how we can do it. The first part is a training. We start from the input, it's XY position and XY velocities, and our goal in the current step, because we use conditional diffusion, and we want to predict the noise that added to the real trajectories that brought us to the current state. So if we will know what is the noise, and according to this loss function, we will know what is the denoise steps that required to find the correct trajectory. So the next part is sampling. We start from initial guess. After it, we take only the trajectories that start from our current position in the maze. We perform all the denoise steps that we found, and from the trajectory, we take the actions that are required to bring the ball to the target.
Okay, so we learned about the setup, the controller, and the diffusion inputs and outputs. Now, diffusion defines the iterative process of denoising, while the backbone architecture executes the denoising step. In this project, we compare how different backbone architectures affect planning performance. We have the MLP with 1.5 million parameters, the one-dimensional CNN with 3.5 million, the transformer with 19.5 million. Now, to address the permutation invariance of the transformer and the translation equivariance of the CNN, we incorporate positional embedding into both architectures. The trajectory horizon is 100, so each diffusion sample will be 100 actions long. This is the overall test we did on the point maze end. First, we have a baseline, which is a classical MPPI controller with no diffusion. Then, for each architecture, we have the diffusion model warm starting the MPPI controller. The diffusion model will generate a trajectory. That trajectory will warm start the MPPI controller, replacing the initial guess. Then, more MPPI refinement steps are done until timeout. To make it fair, each architecture will have the same time budget, and the trade-off is that bigger model will generate better trajectories, but will take more time, and thus have less MPPI refinement steps. This is the first experiment we did, comparing MPPI only in blue and warm starting it with each backbone architecture. In the y-axis, we see the mean episode step until reaching the goal, and on the x-axis we see how much actions are we executing from each plan. As mentioned before, our controller planned 100 actions ahead. The x-axis says how much actions do we execute from that plan until we replan. As you can see, the transformer and CNN achieve better results than the MLP, but unfortunately, with the same time budget, the classical MPPI controller did enough iteration to achieve best results. To conclude, we saw that the CNN and transformer perform better than the MLP, but that for this setup, the naive MPPI controller with no learning at all performs the best. We believe this is because this environment is too simple with only two-dimensional actions, where classical controllers can converge very fast. For future work, we want to test it on more high-dimensional environments. There, the classical controllers are slower and require more iterations. We believe that at that setup, the diffusion can be very beneficial. Thank you, and we will be happy to take any questions.